All right, welcome to my lecture on the hypergeometric distribution. And this is going to be very similar to problems that we've seen in chapter 1. Let me just give you an example. So let's suppose there is a population of 35 individuals, and in this population, 8 of these individuals have a disease. Okay. And we're going to take a sample of just 5 from the population. Size 5. Now, I'd like to remark that of these 8 individuals with the disease, they don't know they have the disease. So they're indistinguishable from the 35 individuals. They could be asymptomatic or just not know. They couldn't have gone to their doctor. And if you were to sample or to come into contact with 5 out of these 35 individuals, what's the probability that exactly 3 out of the 5 individuals have this disease? Okay. So let me write down the question. Okay. So question: what is the probability that out of the 5 individuals exactly 3 have the disease? And I just want to be clear here on what my random variable is. My random variable is x. This is the number of individuals. Out of a sample of size 5 with the disease. And notice that x here is not binomial. There's not a fixed probability. Okay, so that's just one important thing to remark. Okay. So here I'm asking us to calculate probability x equals 3. Well, I think if we go back to chapter 1, probability is the number of ways to select 3 with the disease Okay, then if we have 3 with the disease, we have a sample of size 5, right? So that means we need to select 2 without the disease. Without, okay. And then in the denominator, it's the total number of ways for the experiment to proceed. So and the experiment is to select 5 individuals. There's no reason that all 5 would have the disease. There's no reason that all 5 would not have the disease. It could be that 1 out of 5 has disease, 2 out of 5 has disease, 3 out of 5. So the total number of ways to select 5 individuals. Okay. Well, if we go back to chapter 1, the number of ways to select 3 with the disease, we don't care about order, we just care that they have the disease. That's a combination. So it looks like, well, there are 8 with the disease, so 8, I need to select 3 of them, 8 choose 3, times, I have 35 individuals without, 35, there are 35 individuals, and 8 of them have disease, so 35 minus 8 do not have the disease. And I want to select 2 of them. Okay. Then in the denominator, I'm going to have my total population, and I want to select 5 of them. So 35 choose 5. And that is going to be written, when you calculate this probability, it's going to be approximately 0.06 or 6% chance. Okay. Now let's continue this, and let's just describe this, because there's something more general. So more generally, here's what's going on. There's a population size. And I'm going to call that N. Okay. Of the population size, there are going to be R with a characteristic. So I'll just say with characteristic or trait, there are R of them. There's going to be also a sample size. And let me call the sample size M. Okay. And finally, my random variable X is going to be the number of individuals, not in the population, but in the sample, with the characteristic. And if I want to calculate the probability of X having little x successes, well, when I sample from the population, I'm going to sample M individuals. So there's going to be N choose M. I'm going to take a sample of size M from a population size of size N. In the numerator, I have R individuals with the characteristic, and I want X of them in the sample. So my sample is going to be of size M, and X of them are going to have a characteristic, so that means that there's going to be M minus X of them in the sample without a characteristic. After all, my sample will consist of X with the characteristic and M minus X without the characteristic, so the total sample size will be M. And the population size, they're going to be N minus R of them without the characteristic. This is slightly different than the formula described in your textbook, but it's exactly the same. Okay, I've interchanged which population has the characteristic and which one doesn't, and that's just a formality. Okay, so just a couple of other notes. Is that the mean E of X here, that is going to be this, is going to be N times R or excuse me, is going to be R over N times M. Okay, and this is slightly different because I use different variables than what's in your textbook. And I'd also point out there is no moment generating function. Because the series does not converge. Okay. Let me just quickly give you an example. Okay. One more example of the hypergeometric distribution, and that is in a shipment of 20 parts. Eight parts are actually defective. A mechanic installs 6 of these parts. And it's not marked, hey, this is a defective part. They look identical, so they're indistinguishable from the population. And he installs 6 of these parts. What is the probability exactly 3 defective parts were installed? Well, let's answer this question. And I'm going to just point out that here, I don't refer to the formulas, I just reason through the answer. So I want probability x is equal to 3. And I'm going to install 6 parts. I have a shipment of size 20, so there's 20 possible parts to install, and I want to install 6, to take 6 of those 20 parts. Order doesn't matter, because it doesn't matter whether it's the first or the 6th part installed, it's still installed. So that's 20, choose 6. But it's asking, well, of the 6 parts that are installed, well, what are the odds that 3 of them are defective? Well, I need to pull 3 defective parts from the population of 8 defective. So that'll be 8, choose 3, times, well, I need to install 6 parts. I've already used 3 of them, so 3 remain. I have 20 minus 8 working parts, and I need to use 6 minus 3 of them. When I do this, I'm going to get this probability. The probability is going to be 31.7% that there are exactly three defective parts installed. So let's hope those shipments come in right. Okay. My final note to you just is that this chapter throws a lot of probability distributions. Note, we could not, well, maybe could not, I'll say this, we should not use a binomial distribution here. And because there is no probability of success. Okay. You might say, hey, so this is no, this is not true. Someone might say, hey, if there was probability of success, would it be 8 out of 20? But no, because that's only true for the first trial. In fact, for the next trial, you'd either have to say that'd be 8 out of 19 or 7 out of 19, which shows it's dependent. And that's invalid for a binomial distribution. So my bottom line is, do not use a binomial distribution here. There's no probability of success given, okay? And just keep that in mind. Okay. Other than that, this hypergeometric distribution should be fairly straightforward to use. Okay, thank you.